the gas laws. In the 18th and 19th centuries, they wanted to understand gas, so they looked at it a lot, real hard, with numbers and shit. And then said, what if I do this over and over again? The result was the gas laws. First, they found the variables. What are the values that connect to one another? What things can you change about a gas? The variables are pressure, volume, moles, and temperature. Okay. So pressure we've already talked about a bit. Remember, it's the collision of the particles of the gas with the walls of the container. Volume is the volume of the container. Remember, a gas will expand to fill its container. So whatever the volume of the container is the volume of the gas. N is the number of moles of gas. In fact, the concept of the mole was discovered through the study of gases. And finally, temperature is the absolute temperature of the gas. I want to stress absolute there. When it comes to the gas laws, you cannot use Celsius. Definitely can't use Fahrenheit. You have to use Kelvin. It has to be the absolute temperature, because temperature here absolutely must reflect the motion of the particles. And that means positive temperatures always. So it has to be the absolute temperature, so Kelvin. And remember, Kelvin is Celsius plus 273.15. And this way they discovered 3 different laws. Boyle's law deals with pressure and volume. Charles's law, or Gay-Lussac's law, deals with volume and temperature. And then Avogadro's law deals with volume and moles. So what we're going to do is we are going to look at the law, then we're going to look at the math of the law, and then we're going to use kinetic molecular theory to understand the law. First up, Boyle. So, for each of these laws, we are comparing 2 of the variables. So the other 2 variables have to be held constant. Okay? So we're looking at volume and pressure. What happens to one if you change the other? That means moles and temperature have to remain constant. So what we're looking at here is a constant quantity of gas being held at a particular temperature. And then we change the pressure being exerted on the gas, here represented by these weights, in order to see how the volume of the gas will respond. So if you put more weight on there, what's going to happen to the gas? Well, you're squeezing the gas. You're putting more pressure on, the volume's going to go down. If you remove some of that weight, then the volume will expand. All right. So that is what happens. You increase pressure, volume goes down. In fact, it's a nicely linear, not linear, but a nice directly proportional relationship. If you double the volume, if you double the pressure, the volume gets cut in half. If you cut the pressure in half, the volume will double. Triple the pressure, 1/3 the volume. 1/3 the pressure, 3 times the volume. All right. So, this is how we represent it in terms of math. Pressure times volume is constant. Okay? Or, more commonly, P1V1 equals P2V2. The initial pressure times volume is equal to the final of pressure times volume. So if you double the pressure, you'll cut the volume in half. If you cut the pressure in half, you'll double the volume. What is the final volume of a system that starts at 150 milliliters at 1 atmosphere if you increase the pressure to 1.250 atmospheres? For that, we should go ahead and switch over to a little bit of paint. Come on, laptop, don't fail me now. Okay, so P1V1 P1 V1 equals P2 V2. Okay. The way this sort of problem will work is they'll give you 3 of the numbers and ask you to find the 4th. So it starts at 1 atmosphere. And 150 milliliters. And then we increase the pressure to 1.250 atmospheres. What is the final volume? Okay. So the great thing about these sorts of problems is that you don't have to really do a lot of unit conversions. So long as the units are consistent from one side to the other. Here we start at, we have atmospheres and atmospheres, and our answers will end up in milliliters. It'll be the same, so that'll be fine. So then we cut over to our calculator. We do a small amount of math, and it's really not that bad. Okay. $120. Okay. If you start at 1 atmosphere with a volume of 150 mils, you increase the pressure to 1.25 atmospheres, the volume will go down to 120 mils. Easy peasy, lemon squeezy. Nothing much to it. Okay. Now, in terms of kinetic molecular theory, how does this work? Okay. The moles are constant, okay? Meaning that the number of particles is constant. Meaning that the number of collisions is constant. Likewise, the temperature is constant, so the speed of the particles is constant. So the force of each collision is constant. So the number of collisions is constant, the force of each collision is constant. So the total force exerted by the gas is not changing. However, the volume can change. Therefore, the total area of the walls inside the container can change. That is how pressure will change, or at least how it can change in response to pressure. So if you increase the pressure from the outside, you now have an imbalance. The pressure outside the container is greater than the pressure inside the container. So remember, what we're looking at is this guy here. You have this solid cylinder, and then this piston that can move up and down. Okay. So when you increase the total pressure, you create an imbalance. The force outside, this weight, is greater than the force inside, the force exerted by the gas. So the piston starts to move down. When it does, the volume decreases, therefore the area decreases. Okay. So that means that the pressure inside the container will start to go up because those collisions are being spread out over less and less area. So the force stays the same, but the pressure will go up because the area is going down. Okay. Eventually, the pressure inside the container will be equal to the pressure outside the container, and the piston will stop moving. So that is how you can explain something like this in terms of kinetic molecular theory. Okay, what is actually physically happening? You increase the pressure outside, that causes an imbalance, so the piston starts to move inward, the volume starts to shrink, meaning there's less area, meaning that the pressure inside starts to increase until you get to a new equilibrium, a new equality. All right. So now, Charles's law. Volume versus temperature. This time, we're holding pressure constant, so the weights sitting on top of the piston are staying the same. We're also holding moles constant. The amount of gas inside the container isn't changing. Instead, what we're changing is temperature. Okay. you have a certain volume at a certain temperature. What happens if you increase the temperature? Okay. Well, you know what happens if you increase the temperature of a sealed container. Eventually it's going to pop. That's because the volume is trying to expand. If you heat a gas, it will expand. If you cool the gas down, it will shrink. Oh God, you guys have no idea how difficult this is for me right now. My cat is being adorable and asking for attention. All right. So, the relationship here is volume over temperature is constant. Okay? Or V1 over T1 equals V2 over T2. Okay? So this is different from Boyle's law. Okay, remember, Boyle's law was P1 V1 equals P2 V2, multiplication. Here it's division. V1 over T1 equals V2 over T2. So with Boyle's law, you had an inverse proportionality. Here you have a direct proportionality. If you double volume, if you double the temperature, you double the volume. If you half the temperature, you half the volume. Okay. Whatever you do to one, you do exactly to the other. So, if you have 325 mils at 400 Kelvin, what do you have? What's the volume if you cool it to 300 Kelvin? Now, once again, the math is fairly straightforward. Okay. You have three things, you're being asked to find a fourth. 325 milliliters at 400 Kelvin, you cut the temperature to 3/4, you're going to cut the volume to 3/4. So, 243.75. Again, the math isn't particularly fancy, okay? Not particularly complicated. You're going to have to be able to do, some simple algebra for these sorts of problems. Okay? Identify what variables you're looking at, and thus identify what gas law you're looking at, and then be able to rearrange correctly. Get the correct numbers on top. This one does offer the slight complication that it can look a little. How do I mean weird? Well, like this. V1 over T1 equals V2 over T2. In this particular problem I gave you, we had volume 1 and temperature 1. I gave you temperature 2. And we're looking for volume 2. So when you rearrange that, what you're going to see is V1 T2 over T1 is equal to volume 2. Okay. So that is why it'll look a little weird, because you have T2 over T1. V1 T2 over T1. And thus, if you're not careful, you can put the wrong number in the wrong place because you expect different things to be next to each other. So be careful about that. Watch out for what you're doing there. Don't get them confused in that way. Trust the math. Don't try to intuit what numbers should go in what places. Now, explaining this in terms of kinetic molecular theory. N is constant. The number of moles is constant, therefore the number of collisions is constant. Similarly, dang it, cat. Dang it, there we go. Okay, similarly, pressure is constant. Okay. Now, pressure being constant puts us in a weird position because temperature and volume can both change. Okay. If temperature can change, that means that the speed of the particles can change, meaning the force can change. Since volume can change, that means the area of the walls inside the container can change. So both force and area can change, but pressure has to remain constant. So, in terms of kinetic molecular theory, when you increase the temperature, the particles move faster, each collision is harder, so the force will increase. The pressure inside the container will increase. Once again, we have an imbalance. Okay? When you increase the temperature, you're increasing the force exerted by the particles inside the container. Increasing that force means that the pressure inside the container will be greater than the pressure outside. Okay? So this piston will start to slide outward. It'll start to go up. Volume will increase, and thus area increases. As area increases, the pressure inside will decrease. Okay? Eventually, once again, the pressure inside will be equal to the pressure outside. The imbalance will balance out. The piston will stop moving. Okay? So, increase temperature, you increase the force. This is where the imbalance comes from. The piston starts to move, and thus increasing area. So that's why if you double temperature, you will eventually double volume. And vice versa. If you cut the temperature in half, if you decrease temperature, the force will decrease. That will cause the imbalance in the other direction. The piston will slide in, causing the volume to decrease. All right. Finally, Avogadro's law. Okay. I didn't find fancy pictures for this one in my Googlings on the internet. So this one, you'll just have to visualize yourself. It's rather straightforward, so I don't expect you to have trouble with it. What happens if you put more stuff in the container? It's going to require more volume. Okay, this is kind of a duh one, but they had to investigate it carefully because things can be counterintuitive in nature. It's better to nail things down precisely. Don't rely on your intuition. Your intuition is crap. But yeah, you increase the number of moles, you're going to increase the volume. Decrease the number of moles, you decrease the volume. And once again, it is a nice, straightforward relationship. V over N is constant, or V1 over N1 equals V2 over N2. You double the moles, you double the volume. Cut the moles in half, you cut the volume in half. And this one is stated a little weird, but it's the math is, again, fairly easy on this one. Okay, half a mole occupies 12.5 liters. How much volume do you need for 1.37 moles? Or 1.375 moles. I love you, Cat, but I'm busy right now. I'm sorry. Go play with Wesley. Wesley likes to play. All right. So, once again, V1 over N1 equals V2 over N2. I gave you V1, N1, and N2. What is V2? Okay. So, V2, you do a little bit of algebra, you rearrange, gives you V1, N2 over N1. Volume 1 was 12.5 liters. N2 was 1.375. N1 was half a liter. So we have nearly 3 times the number of moles. It's going to require nearly 3 times the amount of volume. Okay? Nothing too surprising there. Okay? So bringing up the calculator, 12.5 liters times 1.375 moles divided by half a mole, 34.375 liters. So trust the math, trust the algebra, write everything down. I know that's going to be difficult with the way the tests are right now, but hopefully you can power through it. Now, in terms of kinetic molecular theory, again, fairly straightforward. Pressure is constant, so force over area has to be constant. But force and area can, again, change. Now, temperature is constant, meaning the force per collision is constant. But the number of moles is changing, okay? Meaning we're changing the total number of collisions. That's how we change force. Okay? So if you increase the number of moles, you're increasing the total number of collisions, meaning you're increasing the force inside the container. Once again, that gives us our imbalance. The pressure inside is greater than the pressure outside, and the piston starts sliding out. The volume increases, so the area increases because you have more wall. Thus, pressure starts to decrease as the volume increases. Eventually, the pressure inside is balanced out with the pressure outside, and the piston stops moving. So kinetic molecular theory just provides us a framework for understanding the behavior of gas in terms of the collisions of particles. It's pretty straightforward in that way. So those are the three basic gas laws. Dang it, you better not take my sock outside. Don't, dang. All right. Okay, so when we come back at 3:15, we'll finish up what we need to discuss for Chapter 9, meaning that we will start looking at the ideal gas law. Actually, no, I'm just going to go ahead and continue now because this is fairly straightforward. My voice is not yet that dead, so I'm just gonna power on through. I'm gonna just drive straight through on this one. All right. So, the ideal gas law. So, first up, standard temperature and pressure. Remember how it wasn't all that simple for thermodynamics standard conditions because nobody could agree on temperature? The same is kind of true for standard temperature and pressure for gases. All right, standard temperature and pressure, STP, is 0 degrees Celsius and 1 atmosphere of pressure. Except that, no, it's not. It's now 0 degrees Celsius and 1 bar. God damn. But change is slow, so we'll just keep using 1 atmosphere of pressure. It doesn't matter all that much. It's a difference of 1.325%. It's not a... Still, it's annoying. And the textbook notes that this change has happened, but it says we're going to continue using the older definition, 0 degrees and 1 atmosphere of pressure. It's just, yeah, okay. So if they ask you on the textbook, on the test, it could be either one. But I would, just to be safe, I would stick with this one. 0 degrees, 1 atmosphere. So what we're doing here is we are combining the laws. Okay. So Boyle's law said pressure times volume is constant. Just some constant depending on what sample of gas. Charles's law said volume over temperature is constant. Avogadro's law said volume over moles is constant. For each of these, this K for constant, hides what is being held constant. Okay. For Boyle's law, it hides the moles and the temperature. For Charles's law, it hides moles and pressure. For Avogadro's, it hides pressure and temperature. Okay. So for a these are all constant, but they're different constants because they're related to those particular samples of gas. So what we can do is we can combine these gas laws into a universal law. So pressure over volume, or pressure times volume divided by moles times temperature is equal to K, just a constant, an actual constant, because it's no longer hiding those other relationships. Okay, we now have a law that combines all of those things. Okay, and thus this constant will become an actual constant. It doesn't change anymore. It is now a universal. So we're going to go ahead and replace this K with a capital R, the universal gas constant. Okay. This gives you the relationship between pressure, volume, moles, and absolute temperature for any gas, no matter what the conditions, so long as it's an ideal gas. Okay. So PV over NT is equal to R, or more commonly, PV equals nRT. PVNRT. I call it PVNRT because it's fun to say. PVNRT. Okay. And this is the ideal gas law. PV equals nRT. Now, the number will change. The actual number value of R will change depending on what units you're using. So, for example, if it's joules per mole Kelvin, it's 8.31451. Why joules? Well, remember, pressure times volume, pressure times change in volume is work. Okay, we're talking about joules. So the universal gas constant can show up in various situations where you're talking about work. But more commonly, we're talking about it in terms of liter atmospheres per mole Kelvin. So that would be 0.08206, 0.08206. Notice the times 10 to the negative 2. Liter bars per mole Kelvin, 0.0831451. That's one of the reasons why they've changed it to bar. It makes it for a much easier conversion between this sort of thing and this sort of thing. It's just a slight change. Pascal cubic meters per mole Kelvin, 8.31451. Pascal times cubic meters, that is the same thing as a joule. Liter torrs, 62.364. Calories per Kelvin mole, 1.98722. It's going to change depending on the units you're using, because units are just the different scale we're holding up to measure the universe. Okay? Now, the most common we'll be using in this class is going to be this one, 0.08206. Because we will most commonly be working in liters and atmospheres. So when it comes to the math, it can look very complicated, but it isn't particularly complicated. Okay. So what volume is occupied by 2.307 grams of hydrogen at 28.5 degrees Celsius and 775.65 torr? Okay, this one is mean because I didn't put it in terms of moles of hydrogen, I put it in terms of grams of hydrogen. And instead of Kelvin, I gave you Celsius, and instead of atmosphere, I gave you torr. Doesn't really matter. Okay, we can calculate all of those things. So 2.307 grams of hydrogen. We convert that to moles, meaning we divide by 2.016 grams per mole. Our 28.50 degrees Celsius, we can convert that to Kelvin. By adding 273.15. And then 775.65 torr. We convert that to atmospheres by dividing by 760. Okay. So each of those conversions is mildly annoying, but not particularly difficult. So once again, we just bring up our handy-dandy calculator. 2.307 divided by 2.016 means that we are looking... We're looking at 1.144 moles of hydrogen. If you're confused by the 2.016, then you forgot that hydrogen was a diatomic molecule. Okay, so there are two atoms of hydrogen. All right. Next up are 28.5 degrees Celsius. Is 301.65 Kelvin. And our 775.65 torr is 1.0205 atmospheres. Notice that I am maintaining the significant figures here. We started with 4 sig figs for the 2.307, meaning we have 4 sig figs for the 1.144. For the conversion to Kelvin, this was addition, so it's a matter of maintaining the decimal places. And for this conversion down here at the bottom, the 760 is an exact number. It is just by definition 760 torr. So that has an infinite sig figs. So our answer has 5 sig figs to match the 5 sig figs here. Okay. So those are our 3 numbers. Let me go ahead and clear myself some space. Because now we can do our Pevnert work. PV equals nRT. We have pressure in terms of atmospheres. We have moles and we have temperature. We're looking for volume. So V equals nRT over P. So we just plug in our numbers. 1.144 moles. And R is just the universal gas constant, 0.0820578 liter atmospheres per mole Kelvin. Temperature was 301.65 Kelvin, all over our pressure of 1.0205 atmospheres. And thanks to the universal gas constant, our units will cancel out nicely. Moles will cancel with moles. Kelvin will cancel with Kelvin. Atmospheres will cancel with atmospheres, leaving us with liters. And from there, it's just a matter of plugging things into ye old calculator. 1.144 times 0.0820578 times 301.65 divided by 1.0205. 27.75. Only 4 sig figs in the answer. 27.75 liters. So yeah, that's a lot of volume. Gases require significant volumes. That's a very small amount of hydrogen, just 2 grams, 2.3 grams. Nevertheless, it requires 27 liters. At fairly low temperature and pressure. Gases are just expansive. They take up a lot of room. So that is an example of a problem. There are other problems here. I'll leave those as an exercise for you for studying. And with that, we are done with everything of Chapter 9 that is likely to be on the final exam. Congratulations on managing to power through this last portion of the semester. I know it has been difficult. It has been a strain. Whether you found yourself at home with a large family or isolated with no one around you, either one presents different challenges. Congratulations on managing to make it through. I will be busting my hump to get through the work remaining to me for the rest of the semester, and I will be checking my emails to keep in touch with you guys. Good luck on your final.